Okay, it's 11:30. I think I'm going to start with my talk on Hop, a language to design function overload sets. And welcome everybody for joining my talk. Okay, let's go to the outline. First, we give a short prelude on homogeneous variadic functions, how they are used in Blitz and how they were worked on in a series of blocks on Fluent C++. Then we'll look at a historic view and best practices and limitations of those. We take a look on overload resolution of homogeneous variadic functions. We'll check what we can do with concepts. And we will present a small library for really doing homogeneous variadic functions. Okay, in the second part of the talk, we'll look at the library Hop, which expands the library for homogeneous variadic functions by giving you a function parameter building block system. And we'll see how we can define overload sets from them. And at the end of the talk, we will go down into the rabbit hole. We'll see some examples of Hop and we'll look at the internals. So what are homogeneous variadic functions, or HVFs for short? So let's look at some of them. So we may have a logger which takes a bunch of strings, or we have some function max, which takes a range of doubles and returns its maximum. Or we also may have some constructors for some array class or class template, where the dimension is noted in the template parameter, but we still have to generate all those constructors for 1, for 2, and for 3 dimensions. So in the essence, a homogeneous variadic function is a function which takes a non-zero number of arguments, which are all of the same type. And the return type may depend on the number of arguments, but we won't bother with that today. And also, this should work for overloads of those homogeneous variadic functions, which we will especially need for constructors or for function call operators. Okay, so Blitz is a library written by Todd Veldhuizen, and it was conforming to C++ 19.8. And it was pioneering in expression templates. And Blitz has as its fundamental base class that's called array, and it has roughly 48 constructors and 85 function call operator overloads. But if you look at them, essentially 13 constructors are different. And for the function call operators, we have 3 non-const different function call operators and 8 const function operators. And so if we may get in C++ 23, we may get the opportunity to deduce this, then we could also merge this 3 non-const function call operators into the other 8. And furthermore, we have several homogeneous variadic functions repeating 1 to 10 arguments. And we have a lot of similar code in the whole library like that. Okay. In January and February 2019, there was a series on Fluent C++ about variadic functions and how to define them. And it showed different approaches to them and its pros and cons. Now let's take a historic view in C++. So in C++ 98, we would write overload sets manually. So we could write all of them down, and it throws. Okay, it's very explicit. It's easy to write and easy to understand. It's beginner friendly, so no templates or macros required for that. But the cons are, it will only work up to the written number of arguments. So you have to write all the overloads you want to call later. And more or less, it's an anti-pattern. It's like an archetype of don't repeat yourself. So, but with C++98, we could also use the boost preprocessor. So we can write a preprocessor macro for that. The pros, we don't have repetition of code, at least not in our source code. The number of arguments can easily be adjusted. But the cons are, the declaration and the definition of the function is hidden within the macro. This is quite hard to write, and it's even harder to read. And we don't want to talk about debugging at all, because it's a one-liner and debuggers usually step in sense of lines. And yeah. And still, the number of arguments is fixed a priori and is limited by internals of boost preprocessor, which were at that time 256, and today you can go up to 1024. So going on to C++11, we got std initializer list. So we could write an overload just taking an initializer list. The pros, it works for any number of arguments, but it has some cons. So when calling the function, we require additional braces for the initializer list syntax. It's quite inflexible with respect to mutability, or you have to use something like a std reference wrapper. And it may be also called with an empty list. And it's just one argument for the compiler. It's just this single argument std initializer list. So it has different syntax with respect to overload resolution. Or different semantics, sorry. Also with C++11, we got parameter packs. So we can write a function in the sense of give me one t and then give me another set of t's. So the pros, it works for any number of arguments. But the cons, when we write it like this, it will match any input. And invalid input will cause compilation errors or even logical errors, or the worst of all, runtime errors. Okay, also with C++11, we got FreeNA or enable if in the standard, and we could write a function like this where we require at least one argument, and we want all our arguments to be convertible to some given type A. And here the pros, again, it works for any number of arguments. It will match only valid input, and cons are none, at least so far. And the same we can do with C++20. And instead of the FreeNA condition, we use a requires clause. And again, the same as for the FreeNA condition. It works perfect. Okay, let's look into the future a bit. There was a proposal 1219, it got 2 revisions on homogeneous variadic function parameters. And the syntax was, okay, we simply specify some type A, and then we specify the type A with 3 dots, the same as we would do in the template header when we do a non-type template parameter. But here we do it explicitly for the parameters. And the pros would have been it was would have been a native language support for homogeneous variadic functions. And of course, it matches only valid input. But on the con side, this syntax conflicts with var args. And the reason is that the comma before the trailing ... in a var arg function is optional. So this is something that was also new for me. So as you see below, these two functions, foo with an int, comma, ... is the same as writing foo, int, and just ... This is also a var arg function, which is not true for C. For C, only the left-hand side is valid, but C++ also allows the form on the right side. And therefore, the current status of this proposal is simply dead. In Belfast in 2019, it didn't get enough votes to move on. So what's our current best practice for homogeneous variadic functions? So we can use parameter packs plus sphenae condition, or we could use a requires clause. But what about overload resolution and implicit conversions? So let's simply assume we have these two functions. So we have a first function foo, which takes an arbitrary number of ints. I just left out the condition for more than 0. And we have a second overload for foo, which takes a bunch of floats. So let's assume both of those overloads are visible to the compiler. And let's ask ourselves, which one gets called by these 3 calls to foo? And this is where you come into play. I will give you a short call. And hopefully all of you now see 3 questions. And okay. So are you seeing all the questions or not? Okay, let's end. Okay, the minute is over. Let's stop the polling. Okay, so, okay, sorry. I'm not sure. I think you only saw question 3 right now. Okay, let's do it for question 1. So, okay, sorry, was still on question 3 though. This is the first call through with 3 ints. Okay, okay, let's do this quick. Okay. Okay, I'll stop right now. Okay, and let's do also the second one. Okay, this is the call with the 2 floats. Okay, so so let's see what we just got. Okay, I hope you now hopefully see the results for the first call. Okay, we had 75% go for for the int overload, 25% go for it's ambiguous. Okay, I expect the same result for the second call. Okay, there we had one more vote for float. And let's look at the third question, where we had a float and an int. And there we have, okay, that's very ambiguous. Okay, one for float, one for int, and two for ambiguous. Okay. Now I have to mention, okay, this poll was presented by my two hop experts, Luna and Rolf. They wanted to be in the presentation. And I also tell you what my naive expectation was. The first one called the int overload, the second one, the float overload, and the third one is ambiguous. Okay, now let's ask one who must know what's correct. Let's ask the compiler. Okay, so on the left-hand side, we have our two functions and the call. And here we see the first call, ambiguous, the second call, ambiguous, the third call, ambiguous. So, okay, what just happened? Why are all three calls ambiguous? Okay, therefore we have to take a closer look at the two functions. So, first of all arguments we gave to our functions were ints and floats, and they're both convertible to each other, implicitly convertible to each other. Furthermore, both overloads take their arguments by forwarding reference. That's a TS reference. And so they are both perfect matches for those arguments. And then we have a Sweeney condition, but that's just a test if the overload is viable at all. It's not part of the overload resolution. And though the test for both is positive because every int is convertible to an int, of course, and to a float, and the other way around, it's also. So with respect to overload resolution, both overloads are equivalent. They're both perfect matches for the arguments, though they are ambiguous. Okay, so we now got C++20, and we can ask ourselves, can concepts help us out? So when we look into the standard, we see if we want to specify that the compiler selects a special overload by concept, then that overload must be more constrained with respect to the concepts used or the atomic constraints. This would mean we would need something like concepts in the form of some type matches some argument better than some other type. So effectively, this would mean we rebuild the overload resolution with concepts. This may be feasible for two types, but it gets very messy when you have three or more types, and you would have to specialize it on each type you want to use. And furthermore, there's some technical issue. We won't be able to use fold expressions to unfold those concepts and compare them with each other, because when you unfold concepts with fold expression, you will get an atomic constraint. So the compiler won't look into the single constraint of a fold expression. It simply will take it as an atomic. So what have we reached? Our current best practice for homogeneous variadic functions are parameter pack plus Sweeney or requires, but overload resolution is compromised. Whenever more than one of our overloads is viable, then the call is ambiguous and you can't do anything about it. So what's the solution for that? The solution is the overload homogeneous variadic functions have to know of each other. They have to somehow decide which of the both is the better one. So we have to merge both overloads into a single homogeneous variadic function. And that's the next part of the talk. I will give you a step-by-step guide how to do it. So first, we have to provide some interface where we can specify the overloaded types. So in our cases, it would be an int and a float. Next, we have to perform overload resolution. This can be done or should be done by generating all the possible overloads. And then we want to use built-in overload resolution to resolve the call. So there's no sense in trying to rebuilding overload resolution by some concepts or fancy template metaprogramming stuff. You simply won't succeed. And third, we have to report the selected type to the user, or in case it's ambiguous, we will get a compilation error. And here we will use C++17, one C++17 feature for simplicity. And this goes to John Kalb. We will use boost MP11 because he asked us to use boost MP11. So let's go to our first point, providing an interface to specify the overloaded types. We will need a template parameter pack of types. In our case, 2 types, int and float, but we could add more of them, of course. And we will encapsulate them in an MP list, which is a boost MP11 type, which simply packs the parameter pack into type, which makes it easier to handle because now we have a type and not a parameter pack anymore. So how does it look on the call side? So first, we have a list of all the types that are used for overload resolution. We pack them into an MP list and we call that type the overloaded types. Next, we use some helper alias template just to not have to repeat this decal type enable overload type of all the args because we will have to use we have to use it twice. We have to use it in the template to do as a sphere condition, and further on we have to use it inside of the function body to get the selected overload back from this template metaprogramming stuff, and it will deliver us the index of the selected overload. Okay, how do we do the overload resolution? Yeah, so for each type, we have to generate all the possible overloads. So in our case, we have an int, we have a float, and how do we generate all those possible overloads? That's in general an infinite number. We could do it for 1, for 2, for 3, for 4, for 5, but we only have a finite number of viable functions anyway. Only those that have the right arity, which would mean the arity of the actual call. So we will generate one test function of the right arity for each type. So this would mean, in our case, we have to generate 2 functions, one with ints, one with floats. Then we will run built-in overload resolution on those 2 test functions. Okay, and now step back. This is a complete library for doing homogeneous variadic functions in C++17. Okay, so now we'll look at the library closer. So first, we start from the bottom. There we had the enable function. This is the one that is invoked by the caller in the sphere condition, and where we get the types that we want to overload as the MP list. And we also get all the arguments, or the type of all the arguments of the actual call. Okay, and this is passed on to the template overloads. And as return type, we will get this result from this test function. And this will be just an integral constant containing the index of the best matched type. Okay, let's go to the second part of the library, where we create the viable types. So, okay. So this will also be broken down in the next slide. Okay, here, let's look at it. We have this, okay, sorry. We have this type overloads on the bottom without an underline before it. That's only used for unpacking the MP list down here and getting back the types inside, and also getting an index sequence. Okay, this is just, so all the stuff down here is just for accessing the parameter pack inside the MP list. So on the upper half, there we will get all the types, and using, and for each type, we generate a list of types of the desired arity. And this is here this MP repeat of the MP list of types, comma, the arity of the call. This will generate an MP list of the type repeated arity times. And at the back here, we have this parameter pack expansion, which expands the types in here and generates the repeated list for each type. And this, and we will instantiate this single function template with each of those repeated type lists. Okay. Now let's look at the core of that function, of that library. This is the single, oh, no, sorry. Okay, there's one more thing about this line down here. Here we have this using single function template, and back here we have the test function and 3 dots. This is the only C++17 feature in this library, and it means use all the test function from the base classes and bring them into scope. Because we have a lot of base classes all having the test function, the compiler usually wouldn't bring them into scope because it's ambiguous, but by using, we will pull them all into this class and make them visible for the compiler to do overload resolution. Or to be able to call them and then do overload resolution. Okay, so now we're finally at the core of this homogeneous variadic function library, where we generate the test function. And this is quite simple. the single function is instantiated for each of the types we want to do overload with the index of that type in this MP list, and with an MP list params, which we expand down here, which have the type at that index repeated every t times. And we put this params pack in the test function and expand it. And now we have a test function which has exactly the right type and with exactly the right number of arguments. Okay. Yeah. And though this technique of generating test functions you can also find in the SDL implementation, and that's where I also got the inspiration from, because when I tried to match the types by overload resolution, I thought, how does std variant do it? Because there you have this converting constructors where you can have a variant with an int and a string, and you can give it a double, and there it says, okay, yeah, a double matches an int. It's implicitly convertible, and yeah, and that's how variant also does it. They generate all those converting constructors for each of the variant types in a base class, and then select the one that overload resolution matches best. Okay, finally, we have to report a selected type to the user, and in case of ambiguity, return an error, or otherwise we return the index of the selected type, which is of course a compile time constant, which we can thereafter use in template dispatching or in if const expr. So, okay, now let's write on our call side. Here we again have the overload list with the MP list, int, and float. We have our alias template, and now the foo function again uses this enabler with the args and pulls out the result value, which is the index of the selected type. And in case we get a 0, the int type was selected, and we print out, okay, overload int was selected, and for 1, it's a float. Okay, and now let's look at a live demonstration at Godbolt. Okay, so, okay, here's the complete library. So I wasn't lying with the 26 lines of code. The only thing you have to add for simplicity is some using namespace, boost MP11, and we of course, have to include boost MP11. And okay, down here, may make it a bit larger. Sorry for that. Okay. Down here, we have our foo function, and now let's bring the functions back into view one by one. Oh, okay, it's compiling again. Sorry, it was too slow. Okay, so compiling succeeded, and the int overload was chosen with the arguments 1 and 2. Now let's bring the second into scope. Now the float overload was chosen. And now let's try on the third one. Okay, and this will bring an error. And this is exactly how we would like it for homogeneous variadic functions, because in the third case, both overloads are, so the first would choose the int overload, the second the float overload, and none of the two overloads is better in each argument than the other one. And of course, also an empty call will also cause a compilation error. Okay, one thing to note is when I remove the two floats over here, okay, we still get a compilation error. That's because doubles implicitly convert to floats and to ints, and both conversions are equally good because we have truncation of the values. Yeah. Okay, let's go back to the slides. Okay, any questions so far? Okay. Not yet. So, okay, then let's go on. So next, we want to go from homogeneous variadic functions to function parameter building blocks. And this is what HOP was designed for. Though HOP comes from homogeneous parameter sets, and but it was extended to have complete or to have arbitrary parameter building blocks. So the required features for this library is we want to be able to create parameter lists with type generators. Further on, we want to create, or we want to do overload resolution, or we want to create overload resolution conditions from overload sets. And within the function implementation, we want to be able to identify what is the active overload. And we want to be able to access the arguments that were, that the function was called with. But there we also want to be able to get the arguments in the type that the overload was specified with. We'll come to this later. And we also want to be able to specify default parameters, and therefore we also have to have special handling because we have to create them from scratch. So for the type generators, we want to be able to have any CV qualified C++ type. We want to repeat types or type lists. We want to sequence them one after another. We want to do alternatives, just match one of them. We want trailing, non-trailing, defaulted parameters, forwarding references with or without Fine condition, template argument deduction. Also, we would like to adapt existing functions. And finally, it would be nice if we could tag our types to select types and overloads later on easier. So repetition. Therefore, we have a base template called repeat, where you specify a type or a type generator list or type generator, and you specify a minimum and a maximum repetition. So, and as repetition is quite often used, we have a lot of syntactic sugar for that. We have a pack, which simply repeats null to infinity times. We have non-empty packs. We have an optional, which repeats 0 or 1 time. We can also repeat n times. And maybe somebody needs it, an epsilon, which repeats to simply nothing. Okay, sequencing and alternatives. So we want to sequence a set of types or a set of type generators, or we also want to be able to do alternatives. Next, we want to do defaulted parameters. Here we have two styles of defaulted parameters. So we have classical C++ style defaulted parameters, which are only allowed at the end of the parameter list and which behave like standard C++ defaulted parameters. So if you want to specify the one at the end, you also have to specify the one before it. And additionally, we have some initializer template to create the defaulted parameter in case it's not specified by the user. And so the default creation is simply called the default constructor on the type. So, and for C++, for this defaulted parameters, only C++ types are allowed, not whole generator lists. Or you could specify any other creation routine with an operator, a function call operator, which will be called. But we also have what I called a general defaulted parameter, and that can appear at any position in the parameter list, also at the beginning. And this behaves a bit different from the C++ defaulted parameters. It tries to match the argument. If it can match, the general defaulted parameter eats the parameter. Otherwise, it skips it and returns the default created one. So for forwarding reference, this is quite easy. You simply specify a type called forward FWD, and the library will do the rest for you. And we also have like forwarding parameters with conditions. And there we have two styles. We have the forward if in the meta programming style, where you have a template, class template if, which will be called with the current arguments, and has to have some internal function fn, which will then be evaluated. And if it returns true, the condition is met. And we also have a quoted meta function. And if you want to learn what quoted meta functions are, then you should go to the MP11 documentation. So next is template argument deduction. And this did a lot of headache. So we want to have two or even three styles of them. We want to have global type deduction, which is more or less the usual type deduction, where all instances deduce the same set of types. So when we give this a pack of vectors and we want to deduce the value type of the vector, all arguments specified for the pack have to deduce the same type for the vector, the same value type. But we also want to do the opposite way. We want to say, okay, I only want to do local deduction, so deduction only for the single argument, which would mean I could say I want to have a bunch of vectors and all may have a different value type. I only want to be the vector template matched. And of course, we could also mix both, which would mean we have some matching, where an example would be like a map, where you say, I want to match a pack of maps where all maps have the same key type, but they may have arbitrary value mapped to types. Okay, yeah. And here the map example. Okay, the other example was with vector with arbitrary allocators. Yeah. Okay, how can we adapt existing functions? So if it's just a simple function, we can just write adapt from the function, and the library will detect the type of the function and will match against the type of the function, which means when we have an overload set, or we have a template, or we have a function with defaulted parameters, we have to help the library and write some adapter where we do the test by ourselves directly on the function, because for all of those three, the type either doesn't exist, and for a function with defaulted parameters, the default parameters are not part of the function type, though they will get lost when you put them into the adapt at the top. Okay, finally, we have some auxiliary stuff. We want to tag types to refer by a tag name instead of by position. And this we want to do for overloads. And we also want to do for types. So example, e.g. when we have a pack followed by something else, a pack of ints followed by some strings. We want to be able to say to the library, give me only the int arguments back. And this would be done by tagging the int type that we put into the pack, and later on asking the library to only give you those tagged int types back. And of course, we may want to put a Sphene condition on the whole overload set. So yeah. Okay. So here is more or less the grammar of how to build the hop parameters. So you see the repeat alt sequence, the defaulted forward and deduce. And of course, we don't see the adapted stuff because they are not used to build up types. An adapted function is an overload for itself. Okay, and you also see the library only allows to tag C++ types directly. You're not allowed, or of course you can write it, but the library will choke on it when you tag one of the elaborated arguments. Okay, so let's look at some examples. So when we want to have at least one integer, we would write a non-empty pack of ints. When we want to have a list of double followed by an optional options T type, we could write, okay, I want a sequence of a pack of double followed by a C++ defaulted parameter called options T. But we also could put the options T at the beginning, where we have to use the general defaulted parameter because the C++ defaulted are only allowed at the end. We could also write something like a pack of name value pairs, where we have a string followed by a bool, an int, and double, or a string. And this we can have an arbitrary times repeated. Okay, so how can we do like local type deduction? So when we want to have vectors, but we don't care, or we allow the vectors having all different value types, then we would simply write an alias template, which we put into the template deduce local and make a pack out of it. Okay, and in case we want to have a mixed global local type deduction, like a pack of maps having all the same key type. Then we would also write an alias template, which takes the two types for key and map to type for the map. And we also have to define a binding where we bind the index that we want to bind to a certain tag type, which is defined elsewhere. And here we say, okay, the type with the index 0, which would be the first type, we want those all to be the same. And therefore, we call this template deduce mixed, and we give it the binding list and also the template alias, template alias, and it will do the deduction for us. Okay. Finally, we have here a pack of small types. Here we have a forwarding if, which means, okay, we match any type, but it has to be small. So the condition is we want our type to fit inside of a pointer, and we can also do a pack of it. And of course, we can do an overload on all the types we just have seen. Okay. It may not work for, okay, no, it works. You may not be able to call everyone like before. Oh, yeah, okay. Yeah, okay, the two doubles, so those two, they could have been called only with double arguments, but when you now specify only doubles, you will get an ambiguity because both are valid overloads for only doubles. But if you remove one and call it with only doubles, then the one left will be called and not the one with the int overload, because now we have a real double matched by a double, and that's a perfect match, and it's better than implicitly converting a double to an int. Okay. As you may have seen, we have here, though the OL template packs the generated, so the type list generator into an overload. And you may have seen that I dropped the sequence template around it, and that's in the library, you can drop the most outer sequence pattern. You can simply put them in a comma-separated list in here. And of course, we have potential ambiguities that we can do. We can do a lot of ambiguity in here, but if you specify an alternative sequence where the same type appears twice, then of course it's always ambiguous. Or when you try to repeat a potential empty parameter list, so when you try to repeat a pack of defaulted arguments, then of course it's also ambiguous because the library wouldn't know which one of the not expanded positions or you want to use. Okay, now let's go to the second part. So when we just look back, what we did right now here for hop was for when we look back at homogeneous variadic functions, our library, what was the equivalent there was packing two types together in an MP list, or packing types together in an MP list by specifying on which types I want to generate overloads. Okay, now the second part was generating type lists for an overload. So this was for homogeneous variadic functions quite easy. We simply had to do this MP repeat for the arity of the call. But now, for this grammar, we have a more or less combinatorial problem. We have to generate all parameter lists that accept an arity number of arguments from the given grammar. So how can we do this? First, okay, we have to traverse the given definition of the overload recursively, and we have to ensure progress. So we have to generate something for not getting into an infinite recursion. So we have to break out of infinite recursion. So this means for each sub-expression of the overload, we have to first analyze the minimum and maximum length of the type list that can be produced from that sub-expression. And we do this recursively and put it back together. And then we have, for each sub-expression, we know the minimum and maximum number of parameters that can be produced from that sub-expression. With that information, we traverse the overload a second time recursively. And we build type lists, T1 up to Tn, though each T is a type list, not a single type here. And we build those lists for each of the sub-expressions of our expression. So when the sub-expression is just a simple type, then the type list contains only of that type. But when the sub-expression is something more complex, it may be a type list containing a lot of type lists. A type list of length longer than one and containing all the generated parameter sets. And this type list, T1 to Tn, from this list, we have to generate the Cartesian product. So we multiply every type list, or we make the combination of every type list with every other type list. And this gives us a large product. And for each element of that product, we have to concatenate the tuples again. So we have, so from a mathematical point of view, we get a set of type. So each element is a set of type lists from where each type list is a type list generated by one of the sub-expressions. But for the super or the expression that we're currently producing, we have to sequence them all together, or we have to concatenate the tuples. Okay. And furthermore, we have to prohibit infinite recursion. Therefore, we will use the min and max info to limit to type lists that can finally match the called arity. So when we know our type list, the minimum number that will ever be produced from that type list results in, or is larger than the arity of the call, we will never be able to create a viable overload from that. On the other hand, when the maximum is smaller than the number of arguments, that's the same. Okay, and of course, to ensure progress, we have to make sure that we do not repeat empty type lists. That should be. Okay, So let's go to the third part of the homogeneous variadic function library. That's the generation of the test function. And in that case, it was simply unpacking the MP list and expanding the parameters into the test function. Okay, so for the hop library, we have additional tasks here. Of course, we also get a list of types which we expand into the test function, but we also have to take care of templated arguments, which means we have to check for forwarding reference, where we have to generate a forwarding type. And we also have to do local, we have to respect local and global Svine condition. And also we have to call adapters when they are adapted functions. We have to do template argument deduction. And finally, we have to not forget to remove the tag types from the inner C++ types. Okay, so that's roughly how the test function, or that's, yeah, how it looks inside hop. Here we have this invoke, MP invoke with all the if conditions. This is for checking the global conditions on the whole overload against the arguments. We have the deduction helper here, which does the global argument deduction. And okay, at that point, I forgot about the mixed deduction helper, which I added just 2 days ago and which I forgot to put into the slides. And when we look down at the unpack template, here we look at the specified type and the specified argument. And we generate, in case we have a forwarding argument, we generate the appropriate forwarding reference from it. And we also have to check all the local Svine condition for this argument. And we also do local template argument deduction for this single argument. And finally, we also remove the tag types here. So, okay. So let's look at template argument deduction for the test function. Okay, this is the test function for the template argument deduction. That's not the test function that's generated for the overload resolution. Okay, sorry for the name conflict. So in an ideal world, we would have a pack of deduction patterns, which we want to deduce. And we also have a pack of types, T, which are the type of the arguments of the actual call. And we simply put all those types into the patterns and do this for each of the specified patterns. So this would be a really nice and elegant solution for doing global template argument deduction. But unfortunately, in our world, this doesn't work because patterns may be an alias template, and instantiating an alias template with a pack is simply not allowed. Okay, and that's where the Boost preprocessor comes to the rescue. And here we really have to generate a set of test functions for doing the template argument deduction. And I think in the there's the macro, which is the maximum deducible global types. That's only for global types. Oh no, it's for global and for local types. But you can, the global and the local type deduction doesn't interfere with each other. So okay, and in the library, I think this macro is currently defined with 10, though it should be enough. Okay, what else have we to do in the test function generation? We have to keep record of all the formal parameter types, which is more or less the type list that we will generate into the test function. We have also to keep record of all the skipped defaulted parameters. And we have to create a result type from all of this information, which has to include the current index of the selected overload, the generated type list, the skipped defaulted parameters, the locally and the globally deduced types. And that's not all, but it's a quite complex type, the return type from the test function. But the library also has access functions to get the information back you want from the result. Okay, now having told a lot about hop, let's see it at work. Okay, here we have several examples. Let's start with a quite easy one. Okay, that's in the end, it's the same as for the homogeneous variadic functions. And let's put the calls into scope. And okay, we call it with 2 ints and we get back the int overload was called. We can also call it with 2 characters. And again, it compiles, but we see that the types of the arguments are characters, not ints. So because we only output the raw arguments that go into the function, and the function simply takes the arguments by forwarding reference. So you will get the same type as you call it with. And we can also do this for floats and for 2 ints. Okay, and here we see, yeah, the int overload is called, but now we call it with a reference and a const reference. And of course, when we call it with an empty argument list, that's ambiguous. Okay. Oh, sorry. Pull this aside. Oh, look. Where is the talk gun? Ah, it's down here. Nope. That's the wrong one. Ah, okay. Sorry, I have to go. Oh, yeah. Okay. Let's do it like this. Okay. Next one. Here we have an example with where we show that we can also do reference types. So const reference, non-const reference, R-value reference. And again, okay, let's do it a bit quicker. We see, oh, we get compilation errors. And when we look back, the compilation error came from the overload where we call foo with an int and a const int. And we wanted to increase the args for the const int, and that's, of course, nonsense. We have to comment out the increasing of the arg. And then we will see, okay, now we can call our function with reference types. And when we call it with the int reference, we see the input is 5 and the arguments both get increased by 1, and as we call it with n, every time the result of n is 7 at the end. Okay, let's see how we can tag overloads. This is more or less the same example as before, but now we do not select our overloads by index, but we use this has tag template where we ask the overload, has the overload a specific tag, or the selected overload a specific tag, and here we had the tags const L value ref, L value ref, R value ref, and again, it produces the correct output, and we have a much easier and more reliable way to select the right overload, because if we do it with indices and we introduce a new overload, we would have to shift all the indices, or if we forget it, we hopefully get a compilation error. Okay, let's see how we can do with defaulted arguments. Now I have to look where did the, okay, here's the tab. Okay, here we have two overloads. They both have tags again with trailing and leading defaults. And we have, the first one has a non-empty pack of integers. And we also tagged the integers here with a parameter tag. And at the end, we allow a defaulted string argument. And we have the same one for doubles, but with a leading string argument. Okay, now let's see what the bodies of the function do. Okay, we have here the overload for the trailing defaulted, so that's the one with where we expect the int types. And we print out all the arguments from the function call. We also print out all the arguments of the call with, including the skipped defaulted parameters. And finally, we have here an output which selects only the tagged args, and in that case, the args that are tagged with the int parameter tags, and puts out those. And okay, for the double version with the leading defaults, we have the same schema. And now let's bring all four into scope. Okay. Okay, let's make this a little bit larger. Okay, we see for the first call where we specify 1, 2, and hello trailing world, we get out the specified arguments are 1, 2, hello trailing world. The args, including skipped arguments, are of course the same, and the integer args are 1 and 2. Okay, but when we look at the second call where we only specify 1 and 2, we see the specified arguments are only 1 and 2. And when we look at the arguments, including the defaulted ones, we get this hello defaulted world, and this was produced by this default initializer up here. Okay, for the leading defaulted argument, we get more or less the same. When we specify the argument, we see it, of course, in the argument, also as the complete argument list. And down here, we only have the doubles. And when we leave it out, we don't see it in the arguments, of course. Okay. So let's close some of those tabs. Okay, though up to now, we only had one entry point every time. And do we need one entry point to rule them all? No, we don't need it. And this is thanks to also Dreyer, which pointed that out. We have this tag matching where we, if const expr, selected the overload in this global function, but we can also use this tag as an additional Sphinx condition for our function and simply only allow the overload with the correct tag to call that function. So here we again have a very easy overload types. We have a non-empty pack of ints and we have a non-empty pack of doubles. And in the upper function foo, we only want to let in the overload that are tagged with the ints. And in the lower one, we only want to let in the overload with a tag double. And when we run it, okay, we already run it. And when we look at the result, the first one called the int overload and the second one called the float overload. And this makes the implementation a lot easier when you can separate the functions again and not have to implement it in a very large if const expr sequence inside of a single function. Okay, and as final example, I want to show how we can do template argument deduction. And here I selected the mixed deduction, which more or less comprises local and global type deduction. Okay, first of all, up here, there's a helper function to print out the deduced types. And so our example is we have a map type where we deduce the key and the mapped to type. And we also want to do the binding for the deduced mixing on the first template argument, so at T0. And so we want to only allow maps that all have the same key type. Okay, so, and down here we have 3 maps all having int as the key type. So let's compile that. And we see the first argument deduces for the, let's go here. Deduces for the first template parameter an int and also an int for second parameter. And the second argument was a map from int to string, where this is the internal representation of a string in Clang. And the third one was an int to a vector of a double. Okay, now let's see what happens when we try to give the function a map of int and a map of string to int. Then we get a compilation error, but we could fix that when we comment out that and say, okay, now we have map string to int. Okay, now both are equal, but nevertheless, it works. Okay, so let's look at some of the statistics of Hopper. So currently the library has roughly 1,800 lines of code, where the grammar is roughly 150 lines of code. We need 250 lines of code for doing template argument deduction. Test function generator, it's like 300 lines of code, and the argument access. So the test function generator also contains all this combinatorial stuff where we generate all those sub-expression type lists, and it also uses a lot of MP11 stuff like MP11 products on type lists and MP11 flatten, which does the concatenation and flattening the Cartesian product again. And finally, the helper functions for doing the argument access is roughly 400 lines of code. And just to and finally, the test function generator, of course, was this is the core part where we generate the final called test function from the already expanded overload. And the overload generation, where all this MP11 stuff happens, has roughly 400 lines of code, where in the homogeneous variadic function library, this was just calling MP repeat. Okay, so what have we done? We analyzed homogeneous variadic function. How are they supported by the language? We figured out that overload resolution is a problem when we just use the simple standalone implementation, and solved this by merging those in this little library in 26 lines of code. Then we looked at the hop library, where first we saw the grammar for specifying or for building function parameters. We looked at the generation of the type list and how the overload resolution is done, how tagging and accessing of overload works, and there's a lot of stuff more in the library. And finally, what can come next? We could improve, of course, on the type list generation. We can make something like divisibility tests to early exit the generation of overloads when we figure out that it can never match the required arity. We could also check the convertibility of arguments to the type. We could do the is convertible before we add a type to the overload set, and step out when the type is not convertible. But of course, we will do it anyway at the final overload resolution step. And of course, we could use concepts inside the library to create a type system for the internal structure of the library, because currently the use type is an empty list, and this at some point is quite messy when you pack all your support types in a large list. You always have to know at which index which type is stored, and concepts could help here a lot. So, questions, remarks? Okay, we have a question. Are you planning on proposing this for inclusion in Boost? Currently, I would say not. I would like to have feedback from users of this library, or at least not users, but people that look at the library, because currently it's a big hack, of course. I don't know if it's ever useful for anything, except for showing what the language is capable of. But at least okay, maybe I can bring it up quickly. I did an example in Blitz++, and here I have to find the array impl. So this is my own version of Blitz++, and so when we go down here, so okay, here comes the hop part. That makes it a little bit bigger. Okay, so I just replaced 3 of the constructors or the constructor set by an hop overload. And I did it for the default constructor, okay, which is just a single one, but I also did it for the constructor which takes a bunch of ints, which are all dimensions, and also a bunch of ranges, which are also dimensions, but also contain the lower bound. Okay, and so using also this matched tag stuff we just saw, we get 3 functions here for the default constructor. And here we have the constructor setting up the dimensions. So we get all the arguments, and the arguments in the, okay, maybe I show how it looked before. Here we have the default constructor for the length argument as they were before. So we can specify 1, 2, up to 10 dimensions. And at the end, we can specify a storage type. And okay, this storage type is always forwarded, or the storage member variable is initialized with the storage. And then in the body of the function, we simply set the length to the specific length, and setup storage simply initialize the storage from the setup length. And when we look at how is it done in the hop implementation, okay, it's a bit tricky to figure out the storage type because we have to use this. So the storage type got a tag to access this special defaulted parameter, and it will return to us either the default created or the specified storage type. And internally, we set up the length argument by using a tuple for each. This is a function, in my opinion, that's a standard library that's missing in the standard library, which applies a lambda function to each element of a tuple. And the tuple is, as in our example, we return the tuple of specified integer parameters from the arguments and apply each of them to this lambda where the length is initialized by the argument, and then we increase the argument counter. And finally, we call this setup storage. And here we also have to provide the dimension -1. That's how the library works. And we get the dimension by getting the tagged count. So we count how many of those tagged types are in there. Okay, and more or less the same is done for the range overload. Okay. Okay, other questions? Okay, I think I didn't really answer. Okay, so currently I think it's too hacky to be included in Boost. Okay. In case there are no other questions, I'd like to thank everybody for joining this talk and have a nice conference, and hopefully let's hop together. Thank you.